So in our previous meeting, we began discussing redox reactions and how they are different from neutralization reactions. Neutralization reactions involve the transfer of protons, H plus that is, from a Bronsted-Lowry acid to a Bronsted-Lowry base, whereas redox reactions, also known as reduction oxidation reactions, involve the transfer of electrons. Okay, now one way to actually determine whether a reaction is of the redox type is by monitoring oxidation states. We have looked at oxidation states in our previous meeting, or oxidation numbers as some textbooks also call it. But I would just want to rehash what the difference is between an oxidation state and formal charges. Okay, so when we were talking before about calculating the formal charge of an element from a Lewis structure, keep in mind that for formal charge, that's actually assuming that all of the elements in the Lewis structure, all of the atoms in the Lewis structure have an equal electronegativity. Okay, and the formal charge is basically how unevenly shared the electrons are in between these atoms. Okay, so when we actually calculate for formal charge, we're assuming a non-polar covalent compound or a non-polar covalent bonds. Okay, whereas when we calculate for oxidation states, so we're actually assuming here ionic bonds. So for oxidation states, again, it doesn't necessarily mean that if you have a covalent compound, you have ionic bonds. If you're looking for oxidation states, it's just an assumption that if the bonds were ionic, this is how unevenly distributed the electrons are. Like, for example, a higher positive oxidation state just means an element or an atom is more depleted of electrons, and a more negative oxidation state just means that an atom has a greater electron density. So again, here you're assuming an ionic bond. Okay, but again, these are just assumptions, and the true, I guess, charge, air quote charge of an atom in an actual structure is intermediate between the formal charge and its oxidation state. But that's for higher level chemistry. What instead I want to rehash on again will be the rules that we went over yesterday. So basically, when you are trying to determine the oxidation state of an element, number one, in the test, if I ask you what is the oxidation state, for example, of, let's say, H2SO4. If I ask you what's the oxidation state of oxygen here, keep in mind that I'm only asking you for the oxidation state of one oxygen atom. Okay, but if you are determining, let's say, for example, here the oxidation state of sulfur, given that you know the oxidation states of oxygen and hydrogen, keep in mind that each oxygen here contributes its individual oxidation state. Okay. Now, I'll be going again on these rules. And again, basically, what you want to do when you're determining oxidation states is you want to go over elements first with hard rules. And from there, work on elements or atoms in which there are no hard rules. Or you know that the rules are, I guess, bendy, for lack of a better word. Okay, so if you have a pure element, okay, any pure element, remember that an element is just composed of a single element, or, well, yeah. If you have a pure element, it can be a diatomic, polyatomic element. I guess that's what I'm trying to say. Pure elements have a zero oxidation state. Pure elements are neutral, okay, and therefore they will have a zero oxidation state. Okay, meaning they have all of their electrons intact with them. If you're looking at oxidation states again as a measure of how deprived an atom is of its electrons. Okay, so let's say for example all of these have oxidation states equal to 0. Okay, sulfur 8, each sulfur there has an oxidation state for sulfur equal to 0. Okay, I think I provided also other examples before, such as phosphorus 4 or bromine 2. Phosphorus and phosphorus 4 has each phosphorus with an oxidation state of 0. And for bromine 2, each bromine has an oxidation state of 0. Okay. Now, when you have ions, in particular monatomic ions, if you remember that the charge of an ion actually tells you how much electron has either been gained or lost by an atom. So for monatomic ions, it is therefore fitting that the oxidation state is equal to their charge. So for example, magnesium 2 plus has an oxidation state of +2 because it was removed or stripped of 2 electrons. Okay. Let's say for example, transition metals have various oxidation states. Let's say vanadium. Vanadium 5 plus can this vanadium 5 plus has a +5 oxidation state. Okay, oops. Whereas other forms of vanadium ions, let's say for example V2 plus, this one has a +2 oxidation state. And this, okay, and then the next one will be perhaps this is the strictest rule. If you have fluorine, okay, unless you have diatomic fluorine, then the oxidation state of fluorine will always be -1. And this is because fluorine is the most electronegative element. That's it, period. Okay. Now, if it bonds with itself, then there's an even sharing of electrons because fluorine, two fluorine atoms have identical electronegativities. Okay. Another hard but a little bit relaxed rule is for oxygen. For most compounds, since oxygen is after fluorine the next most electronegative element, oxygen will have an oxidation state of -2 for most compounds. Now again, there are a few exceptions. Number one, if oxygen is bonded to fluorine, as we have discussed before. So if you have, for example, something like this, then the oxidation state here of oxygen should be +1. Okay? Because again, fluorine will have an oxidation state of -1, except only if you have fluorines from diatomic fluorine. Okay, and then the second exception will be if you have these compounds called peroxides. Okay, peroxides are basically compounds, ionic compounds, that are formed from the anion O2 2-. Okay, if we were to apply rule 2 for this peroxide anion, then you will actually notice that each of those oxygens has an oxidation state of -1. Now another exception for oxygen will be superoxides. Superoxides, on the other hand, are also ions. Okay, they can form ionic bonds too. So superoxides have this structure. Okay, now, so you can see you have 2 oxygens and the overall charge is negative. Okay, we have not been to that rule yet, but each oxygen here therefore should get a -1/2 oxidation state. So in other words, oxidation state can actually be fractions, by the way. Okay, there's no rule actually saying that they cannot be, that they have to be strictly whole integers. Okay. Other halides in group 7 will also have -1 oxidation states for most compounds. But again, the exception is if they are bonded next to atoms which are more electronegative than them, i.e. oxygen and fluorine. Okay? So let's say, for example, if you have this ion, the hypochlorous ion. So here, oxygen should still have -2, and fluorine here should just be +1, meaning fluorine is actually more devoid of electron density, just because oxygen is more electronegative than it. Okay. Another rule is the oxidation state of hydrogen in most compounds is +1, except if you have the hydride species. Hydride species are basically ionic compounds, again, with the hydride ion. The hydride ion is H minus. Don't confuse this with the proton, because the hydride ion is not only a proton, it is a proton plus an electron. Okay? In which case, if you have the hydride ion, then the charge of hydrogen is -1. I take that back, actually, because hydride is not only a proton, it's actually composed of a proton and 2 electrons. Okay, again, 2 electrons. Hydride has 2 electrons. Okay, and then and then the last rule, which I've been actually doing all along anyway, I'm not sure if you caught it, is that if you have a polyatomic compound, be it an ion or a compound, then the oxidation state, the sum of the oxidation states should be equal to the charge of that compound or that polyatomic ion. Okay, let's say for example, if you have a neutral compound, perchloric acid. Okay, so for perchloric acid, the total sum of the oxidation states must be 0. Okay, so what you do then first is you identify hard rules. So here, oxygen will always be -2 because it's not a peroxide, superoxide, or bonded next to fluorine. But you have 4. So this one is -2 times 4, that's -8 from all the oxygens, the contribution. And then you have hydrogen, which we said again, unless it is an anion, will always have a +1 charge. Okay? If we add +1 and -8, it's a total of -7. And therefore the only one here we don't know is chlorine. Okay, now for chlorine, in order to get rid of -7 from these two, the number that you will add to -7 to get a sum of 0 will be +7. So there you go. And then of course, if you have ions, as we will demonstrate again in another example in the next slide, you have to make sure that the oxidation states add up to the charge of the polyatomic ion. So let's work on these examples that we have done earlier. What I'm going to do differently is I'm going to show you some small math equations that you might find handy in case you're having a hard time trying to do a mental math of what the oxidation states are of an element that you're looking for. Okay. So for example, let's go to lithium oxide. Okay, now remember, the first thing that you want to do is, okay, what is the charge of lithium oxide? So here, lithium oxide is a neutral compound, so the overall charge should be 0, which means that the sum of the oxidation states of each and every element here, meaning that oxygen and those 2 lithiums, I repeat, those 2 lithiums, not just one lithium atom, there's 2, should be equal to 0. Okay, now the next thing that you do, identify atoms with hard rules. So here we have oxygen, which is always -2. Now you ask yourself, if the oxidation state of oxygen is -2, okay, and then you have 2 lithium ions, oxidation states of which you don't know, what will be that oxidation state if you add these together? Okay, so this is the oxidation state, by the way, of lithium of lithium, sorry. I think I gave away the answer there. If you add these 2 numbers together, what is x so that it will be equal to 0? Okay, so if you do the math, that will just be 2x is equal to 2, x is equal to +1. Alright, so therefore the oxidation state of each lithium here is +1. And check, the +1 times 2 is equal to +2. +2 times -2, or +2 plus -2 is equal to 0. So again, that's +2 plus -2 equal to 0. Alright, let's do the next problem. How about if we have nitric acid? If you have nitric acid, again, look for hard rules. So harder rule here will be for oxygen. So oxygen is always -2, okay, except some exceptions. And then here hydrogen should be +1, okay? Now what we don't know is nitrogen. Okay, so let's set up another math equation. Again, all of these oxidation states should add up to 0. So this one should be, you have 3 oxygens, each carrying a -2 oxidation state. Okay, plus you have 1 hydrogen carrying a +1 oxidation state. Okay, plus you have 1 nitrogen with an unknown oxidation state. Again, when you add them together, that should be equal to 0. So this should be -6, okay, plus 1, okay, plus x is equal to 0. X should be equal to, therefore, +5. Okay, this will add up to be -5, and then if you transpose that to the other side of the equation, you get +5. Okay, this is 6. Alright, so that should be +5 then. And again, if you do the math, all of these numbers, again considering these subscripts too, should line up and add up to 0. Okay, so the last example, let us review the dichromate ion. Okay, so for this one, again, hard rules. Well, I mean, there's only 2 elements here, so let's go for oxygen, -2. Now for this one, remember that this is a polyatomic ion, and you want to have the sum of the oxidation states to be equal to -2 this time. Okay, now you don't know what chromium is yet, but you have 2 atoms of chromium, okay, with an unknown oxidation state that we're trying to figure out. And then plus you have 7 of oxygens, which you know the oxidation state is -2. That's equal to, if you sum all of them together, -2. Okay, so this is just going to be 2x minus 14. 2x minus 14 is equal to -2. If we transpose -14 the other side of the equation, or if we add +14 to both sides of the equation, we get 2x is equal to plus 12. Alright, and then x will just be equal to +6. Okay, and that's basically how you determine oxidation states, because so this is the oxidation state of chromium.